Institute of Engineering and Technology.
Hello students, good morning. Today I am going to start a whole new chapter from your Mathematics 2 subject, which is Fourier integral. This talk is about extension of Fourier series. In your last semester, semester 1, you have seen how to consider Fourier series for any random function. In that, we have seen how to convert any function in form of sine and cos. Today we are going to extend the same concept with help of integration. As all of us know, the series is nothing but the summation of infinitely many numbers. In this chapter, we will learn how to convert that summation into integration. So, Fourier integral is actually the refined form of Fourier series. This series of lectures in this chapter of Fourier integral is divided into three parts. There are only three parts in this chapter, and they are almost similar to the case of Fourier series. First part is Fourier integral general case. Second part will be Fourier cosine integral. Third part will be Fourier sine integral. In this talk, we are considering Fourier integral general case. So let us consider Fourier integral of f of x, which is defined by f of x from 0 to infinity a omega cos omega x plus b omega sin omega x d omega. Here you can see clearly that I replaced summation from n equal to 0 to infinity from Fourier series into integration. In that case, it was a0 by 2 plus summation from 1 to infinity on an cos n pi x by l plus bn sin n pi x by l. Whereas over here, I considered all possible coefficients into single integral sum. An's are replaced by a omega, bn's are replaced by d omega. And there is nothing like length L in this calculation. So more general format of Fourier series is Fourier integral. Here we are defining a omega and b omega as Fourier coefficients, or Fourier integral coefficients. The first integral coefficient a omega is 1 over pi minus infinity to infinity f of x cos omega x dx, and second coefficient is 1 over pi minus infinity to infinity f of x sin omega x. This simply means that they are almost similar to the coefficients of Fourier series. Now let us consider example. Using Fourier integral, prove that this integration is equal to this function. Now, they can ask you directly to find Fourier integral for the given function, or they can ask you a question in this part in form of through the statement. So here, the first thing which I want to consider is that if I consider this as integral of something and this as function of something, then I want to find Fourier integral for this function, which will result into this. So clearly, if I go to the previous slide, You can see here f of x is integration of something into cos omega x, something into sin omega x. Coming back to this example, here also you can see there is a function on the right hand side, that is 1 upon 1 plus omega square into cos omega x plus omega upon 1 plus omega square into sin omega x. So it will be very easy for us to prove that if I consider this function and if I find its Fourier integral, then a omega will be 1 over 1 plus omega square, b omega will be omega upon 1 plus omega square. Then using the Fourier integral, you can say that left hand side over here is equal to right hand side. So let us begin our Fourier integral. As I told you that we are keeping this integration in our mind while solving this example. So focusing first of all on a omega, the formula for a omega is 1 upon pi minus infinity to infinity f x cos omega x dx. Considering given function, I am dividing the range of minus infinity to infinity into two parts. 1 upon pi minus infinity to 0 is 0 cos omega x dx plus 1 upon pi 0 to infinity, which is pi e raised to x cos omega x dx. Let me go to this function. For x less than 0 it is 0, for x greater than 0 it is pi e raised to minus x. The single point x equal to 0 will not make any contribution in this calculation, as we all know that integration is all about finding area under the curve, and to take a single point, then the area is considered to be 0. Now let us move further. The first part is 0, obviously as this integration it is under value 0. In the second part, I am taking e raised to minus x cos omega x, I am taking pi outside, and then using the formula e raised to ax cos bx as e raised to ax upon a square plus b square, a cos bx plus b sin bx. Value of a is minus 1, value of b is omega. So this equation will take e raised to minus x upon 1 plus omega square minus cos omega x plus omega sin omega x with range with the limits 0 to infinity. Taking the values into x. So if I put x equals to infinity, to give me e raised to minus infinity. That means it is 1 upon e raised to infinity. Now we know that e raised to infinity itself is infinity. So 1 upon infinity is considered to be 0. So the first limit over here is 0. Okay. Minus, we are taking x equals to 0. So e raised to 0 will be 1. So it is 1 upon 1 plus omega square. Cos 0 is 1. Sin 0 is 0. So ultimately, its value is 1 upon 1 plus omega square. Now finding value of b. As we did in case of a omega, similarly I am taking the value of b omega. The only change is cos is replaced by sin omega x. With similar arguments, I am using the formula of e raised to ax sin bx. So it will give me e raised to ax, a square plus b square, with a sin bx minus b cos bx. With a equal to minus 1, b equal to omega, will give me e raised to minus x upon 1 plus omega square minus a sin omega x minus omega cos omega x. Again, taking limits 0 to infinity. The first part will be 0 as e raised to minus infinity is 0 minus taking x 0 sin 0 0 cos 0 is 1. So it will give me 1 upon 1 plus omega square into minus. Therefore, b omega is omega upon 1 plus omega square. Taking these two values into our Fourier integral will give me f of x 0 to infinity 1 upon 1 plus omega square cos omega x plus omega upon 1 plus omega square sin omega x d omega. That indicates, if I write down this function as our assumed function, and if I write down this integration by taking 1 plus omega square common in denominator, will give me the desired integral. This simply means that if I want to find integration or Fourier integral of this function, if I want to find Fourier integral of this function, it will result to this answer. Now, the question would be that how to consider different functions for Fourier integral, or how many types of functions can be considered for Fourier integral. So the whole process depends upon your integrable ability. If you know how to solve integration for various functions, you can find Fourier integral for almost all functions. The only requirement is it must be a piecewise smooth function. So this is all about my first part of Fourier integral, which was the general case. In upcoming videos, I will also discuss special cases like Fourier sine integral, Fourier cosine integral, and later on we will also discuss that how to figure out in exam that which example is falling under which category. I hope you now consider this first part as a general case, and if you know how to solve example using general case, the rest of the methods are just a special cases of this. It won't make any difference if you apply directly this general case to all examples of Fourier series, Fourier integral. I hope you understood this technique of Fourier series, Fourier integral in general sense. Thank you.
LJ Institute of Engineering and Technology.